Okay, so I'm starting here with this coordinate grid because in this section, we're going to focus on this function, x squared. And really, this is going to be the entire focus of this entire unit of chapter 3. This is called a quadratic. Okay, quadratic. This is known as a quadratic function, the function being f of x, and the fact that I'm going to be able to graph it. Okay. So before I get too deep into this graph, because we will be focusing on this graph to begin with, just to give you the notes, like the headline version of what we're going to be doing for today. So these are, we'll be doing section 3 notes. These are uploaded onto Google Classroom right now. Just to kind of break down our title information, the name of this unit is Graphing Quadratic Functions. Okay, so first off, graphing. We will be doing visualizations of these functions. So one thing to just prepare you for, it may come in handy to have some graph paper for this unit, because we will be graphing quite a bit, and it can be a real pain to draw all those coordinate grids over and over again. So if you do ever need graph paper, I do have plenty here on site, and you can just email me and I can make sure I can get you however much you need. Okay, but we're going to be graphing now. Quadratic functions, this is going to be a new term for us. Quadratic is going to refer to x squared. Okay, x squared. So we are dealing with an exponent in this in these types of functions, but this will be basically the base of every function that we're dealing with in this unit. X squared. That's what we're going to refer to as a quadratic. So in your notes, if you need to, next to quadratic, you can put in parentheses or whatever, x squared. Okay, so quadratics, you're going to deal with x squared type of functions. And the function part, again, kind of refers back to graphing. The function just means it's not going to do anything wild and crazy on the coordinate grid. And we're going to focus on the stuff that's more of the simplified version of within this family, within the quadratics. Okay, so these notes get really busy really quickly. So I wanted to simplify things a bit, back off a bit, and just simply talk about the most basic version of a quadratic, and that being the x squared graph. Okay, so let's explore real quick, what is a quadratic? What should it look like? All right, so this is the most basic version of a quadratic, an x squared type of function. Just an x squared, no other business going on off to the side, no coefficients multiplied in front, just x squared. What will x squared do? Okay, and so here's where, again, I will remind you, anytime you are asked to graph a function, one thing you can always do is create an XY table. Okay, basically, if I throw enough x values into this function and do the computation part of that, I'm going to get a bunch of y coordinate results. So what I'm creating basically by punching a bunch of values into this x is I'm creating a bunch of x values wherever they may be located on a coordinate grid. And if I get enough, then I have the entire shape of the graph. Okay, so one thing we're going to explore is what's the fewest number of things that I can plug into this to get the shape of whatever it is that I'm looking for, a quadratic. Okay, and so we'll explore that. But essentially, for right now, let's just start plugging values in and seeing what pops out the other side. So for instance, with any function, if I were to plug in x equals 0, here's my x-axis. What I'm basically doing is when I plug in x values is I'm plugging in various positions on the left-right part of this coordinate grid, and I'm finding out how far up or down they go, depending on what pops out the other side of this function. Okay, this goes way back into like when you first started graphing and that sort of thing. So just to kind of finish this off and put our labels here, there's my x-axis, and here's my y-axis. All right, so when I plug in an x value, like say x equals 0 right here. So I'm basically at this point, if I were to plug in x equals 0, I'm finding how far up or how far down the coordinate grid that value will go. So if I were to plug in x equals 0, let's go ahead and draw a little coordinate, or not coordinate grid, a little xy table right here. All right, so an x, y, or xfx table right here. Okay, I'm going to plug in a few different x values. Let's just experiment with a couple. All right, so let's try putting in like a negative, like -1, positive, like that. We'll plug in a few different values, a little bit of a spread here. I'm always curious what negatives do in a function. I'm curious what 0 will do. I'm curious what positives will do. This is a decent spread right here. Again, I can add whatever numbers I want to this x column right here. And all I'm doing is I'm plugging them into this function to see what pops out the other side. Okay, well, let's start with 0. Okay, if I were to plug 0 into this function, let's see what happens. Well, when I plug in 0, basically I'm plugging in into this x squared and replacing the x with 0. So in this case, I would end up with 0 squared, right? I'm just plugging in that value. Well, if I square 0, I get 0 times 0, or just 0. Well, what we've just created is a coordinate point. Okay, let's use a different color. I've just created a coordinate point. When x is 0, y equals 0. Well, that's a coordinate point. And so if I were to graph the coordinate point on this coordinate grid, I'd find 0, 0 right in there. And that coordinate point is definitely part of whatever this function may look like. And if I do this enough, basically I get the shape of the graph. So if I were to plug in -1, again, doing the math here, if I were to plug in -1 for x, I'd do -1 squared. Well, -1 squared is the same thing as -1 times -1, which will cancel out the negatives. I'm going to get +1 on the other side. And again, what I've just created is a coordinate point. When x equals -1, y equals +1. And I've just created another coordinate point. So -1 would go left 1, +1 would go up 1. That is definitely on whatever the shape of this graph is as well. And I'm going to keep going, but if I were to plug in this +1, that would be the same thing as saying like, all right, well, now that +1 squared, and 1 times 1 is a +1. You'll see that similar to what we saw with absolute value graphs, I'm seeing this kind of reflection, this symmetry. But again, I've created a coordinate point. So when x equals +1, I get +1 on the outside, right? So then I would go right 1 and up 1, right? And so now I see a little bit of what my function would look like. Now, even this is not a ton of information. All I'm seeing here is that there's some sort of, triangle type of shape. This definitely not linear where we keep going in one direction. It bends in some way. But now we have to kind of, if I were to keep putting values into this, I would get a more definitive shape. So this, for the record right here, is stuff that it's on my solution sheet that's uploaded on the Google Classroom. This is an example of what you would do for an XY table. But now I'm going to go back up top here and just start visually doing this, because some of that stuff we can do in our head because we're just doing this simple operation, this x squared. Well, let's see what happens if I were to plug in x equals 2. If I were to go to the right and plug in 2, what would happen on the other side? Well, if I do 2 squared, that would give me 4. 1, 2, 3, 4. And so I get this as a result. Okay, so this one went up 1 over 1, but this one then went up over 1 and then went up 3 more. So it's accelerating this direction. Now, if I were to plug in -2, right? If I were to plug -2 in here, -2 squared is the same thing as -2 times -2, which will make it positive, and I get a +4 here as well. And I end up with this result. And so we're seeing this kind of V shape, but it's not really a straight V because these points I wouldn't be able to connect with a straight line. It curves. You see that? If it were a straight line, this straight line would go off like this way. You see how it wildly misses that point? Or if I were to connect these 2 points, see how it misses that guy? Okay, so it's not linear. It's curving. Well, if I were to plug in 3, if I were to plug 3 into this value, 3 squared gives me 9. And so I would go 1, 2, 3, 4, 5, 6, 7, 8. Basically, I'd be up here off the screen when I go over to 3. And so what you're seeing here is that it's going up slowly, but it's quickly accelerating. And so we end up with this kind of shape. Okay, we end up with a curve, right? So this is fundamentally different than an absolute value that we saw in chapter 1. And then we see what we find out is that we end up with the same kind of shape on this side, because if I were to plug in -3, I also get 9. And what you end up seeing is you get matching points across from each other. Okay. And what we end up with fundamentally there is what we call symmetry. Basically a mirror reflection of one side over to the other. This is an x-squared quadratic function, okay? This is a quadratic. So here's that term again. Quadratic. This is a quadratic function. It's going to have this U shape, right? U shape. So that might be another thing to put in your notes. This is going to be a U shape. So one thing you're going to be asked to do in several of your problems is you're going to be asked to compare your various quadratic functions back to this one. This is the most basic quadratic function, okay? A simple x squared. And I could keep expanding this. For instance, I only did whole numbers. I could do decimals too, but what would I find if I did like -1.5? So like right in between here, between -1 and -2. If I were to square -1.5, I would get +2.25, in case you were wondering. But that would give me about here, okay? And what you would find is that even if I went decimals and fractions in between things, I would match this curve, okay? So I did 5 coordinate points for this function. There are obviously an infinite number more, because that's why I connect the dots with this curve. But in general, one of the main punchlines to get out of this lesson is that quadratics are x-squared graphs. And what will they look like? They're going to have this U shape. Okay, and this will ultimately be the parent function that we're comparing a lot of these graphs to. Okay, so let's move on from this real quick. I'm going to go back to the notes, because now I'm going to move through a lot of the key terms that you are going to see. Okay, this will move by fast now, so try and keep up here. So back to our notes. Again, these are uploaded onto Google Classroom. There's a lot of information here, a lot of valuable information. So let me just kind of break down some of the key points here. Again, main punchline to understand. A quadratic function means that we're talking about these x squareds. What will an x squared look like? What should it look like? I'm going to get this U shape, this curved U shape, right? It's going to be curved because of the exponent that's happening right here. The exponent causes things to accelerate in one direction or the other. We saw the same thing with exponential graphs, exponential functions. The difference there was that I had my variable x in the exponent, as opposed to this where x is now in the base, and it's always going to be squared. Okay, those will be quadratics. A couple other terms to be aware of. Parabola, you're going to see this term a lot. Parabola. You heard me mention yesterday that this is one of the most naturally occurring shapes that we see, partially because of gravity. What do I mean by that? You'll hear terms like parabolic motion, parabolic function, right? Parabolic motion. Another way to describe that for those that end up in like higher level science classes, like say physics, is another way we describe it is called projectile motion. Basically, anything thrown, anything falling is going to generally follow a path of a parabola. And it may seem, maybe confusing, because you're like, wait, this is a U shape. Nothing falls in the shape of a U. But here, let me quickly show you this other item I have here in the margins. Okay. So real quick right here, I distinguish between a positive parabola, a positive quadratic, and a negative quadratic. We see the same thing that with lines and slope, right? I have positive slopes versus negative slopes. I can have happy face U's, happy face parabolas, happy face quadratics, and I can also have sad face or negative quadratics, negative parabolas, those sorts of things. This tends to follow a lot more closely the path you may be thinking about when something is thrown or launched or whatever, okay? This is a familiar path for people that watch sports, okay? If you were ever to see like a basketball get shot or a baseball get hit, a football get thrown, okay? tennis balls get hit, whatever it might be, it tends to follow a similar type of arch, a similar type of curve. Now, obviously, this can be a much shallower curve depending on how hard it's hit or thrown or whatever it might be. In that case, this would be like something like if I was standing right here and I threw a baseball into the air, like pretty straight up into the air, it would follow this kind of path. This is called projectile motion. And the reason why it takes this shape is actually a simple reason that for those that end up in a physics class, you'll discover this real quick. But gravity, the way gravity affects things getting pulled back towards the earth, it's a quadratic function. Basically, there's an x squared in there, meaning it's going to take on this shape. Okay, so by what do I mean by like seeing this most often in nature? Like anytime you throw something, it's going to follow a parabola type of shape, right? This may also be a familiar type of shape for things like bridges. Okay, because from an architecture standpoint, this tends to be a very stable, strong shape because of how it is shaped. Okay, another way we might see it is like satellite dishes. Satellite dishes also have a parabolic type of curve to them because of how they'll receive information. But some of that stuff we'll get deeper into later in the unit. For right now, I just wanted to kind of introduce you to the shape again. Okay, so again, you're going to see this term parabola or parabolic. That also refers to a quadratic function, or more importantly, x squared in terms of formula, right? So let me just breeze through a couple of key terms here. All right, a couple of key terms here. Decreasing and increasing. Obviously, you'll likely know what increasing and decreasing means, but in terms of my function, all parabolas, all quadratics, all x squared functions will have this kind of U shape. All of those shapes will have a portion that is decreasing and a portion that is increasing, fundamentally just based on the shape of it. Okay, like in this case, if I were to think about like the slope of a line, like reading a book from left to right, right? If I were following the slope of this, reading it like a book from left to right, this is obviously going down. That's what we would call decreasing. On the other side of that, it's increasing and going up. Okay, so also be aware that reverses in the case of a sad face parabola. Now, this is just like the example above. There's my decreasing side. It's increasing after that, reading it like a book, left to right. In this one, now it reverses. Now, in this case, it's increasing on the left side, and now it's decreasing on the right side. So it just reverses there. Be aware of that stuff. Okay, next term to be aware of. Arguably one of the most important terms, so definitely highlight this guy. Circle it, highlight it, whatever you need to do. Vertex. This is a term we've come across before, particularly when we dealt with absolute value functions. But vertex for us is going to basically be the extreme point of our U-shaped parabola. Okay, for this happy face parabola, the vertex is the lowest point. If it had been a sad face parabola, like this one, the vertex would be the highest point. So either the peak or the valley, depending on what, whether it's opening upwards or downwards. Okay, vertex. And then the last term I wanted to talk about real briefly was Aos Axis of Symmetry. Okay, we explored this in the very beginning when we were dealing with those with that one graph that I did. When I described it being symmetrical, or like there was a mirror down the middle of it. Okay, the axis of symmetry represents, like, again, mirror is a good term for the term symmetrical. Okay, but it's this idea that on this right side of the graph, these points right here are perfectly reflected over that mirror to the other side. Okay, and because it's a symmetrical shape, because both sides have the same kind of curvature, the same kind of distance away from the mirror, right? Because it has that shape, the axis of symmetry, the reason they call it an axis is because it's this vertical line. We'll deal with some that are horizontal in the future, but for right now, let's focus on the vertical. You'll find the vertical line, it's going to go through the vertex. That'll be an important thing to understand. Axis of symmetry will always go through the vertex, whatever extreme point it is, whether it's a happy face one like this one, or if it were upside down and went the other way. In either case, the axis of symmetry splits it in half. Okay? All right. So next thing I want to do is I just want to give a couple quick words about the actual title of our section here for section 1. Notice that's A, times x squared. Now, we're always going to be dealing with this kind of family of functions. So we're always going to be dealing with an x squared version of functions. That will always be there. So this a in front represents some coefficient or number multiplied by my variable. And so what this section purely explores is what will this number, how will this number affect the shape of that x squared u shape that we talked about? And there are two ways that it will do it. Two ways that a can affect the shape of this u. Okay, first thing, the first way has to do with what we would call the magnitude of a. Basically, how big is a, right? The bigger this number is, 100, 1,000, 1,000,000, doesn't matter. Like if it gets really, really big, that makes it steeper. And so a directly affects steepness. Okay? It's kind of like slope. The bigger the number, the steeper the line, right? And so in this case, the bigger a is, the steeper it gets. So for instance, this guy right here, and this seems really busy here in the margin, but this thinner parabola, this thinner u, this thinner quadratic is the 3x squared function. Now, notice that 3, that coefficient in front, is like a steep slope, right? If I gave you a line that had a slope of 3, that would mean I go up 3 over 1. So it's steeper than a regular one slope line. Okay, it makes it steeper. Had I made a even bigger, like 100, it would pinch that even tighter. Okay, it would make that so steep, it would almost seem like it closed down on itself. Okay, the bigger a is, the steeper it gets. On the flip side of that coin, the closer to 0 that a gets, the wider it gets, the more shallow is another way to describe it. And so in this case, you see I had 1/3 x squared. The closer to 0 that gets, the smaller the fraction, the wider that parabola gets. And so this one right here, this little dotted pink line, might look a little bit more like a satellite dish to you, right? Because our satellite dishes have a very, very shallow slope to them, right? And so they're still parabolic. It's still x squared, as you can see with that function. But the coefficient, the a, the number in front, was really, really close to 0, which widened it out. It made it shallow, or it took this parabola and it stretched it wide. Okay? So a can affect the steepness. The bigger a is, the steeper it gets. The closer to 0 that a gets, the shallower it gets. Okay? So a affects the steepness. The other way a affects it's a little bit simpler, okay? And that has to do with whether it's happy face or sad face, okay? And this simply has to do with whether it's positive or negative, okay? And so this one's a lot simpler version. If a is positive, if a is bigger than 0, so it's positive, and maybe it helps to write positive off to the side. If a is positive, we get a happy face, positive, happy face, positive, happy face. And so we get an upward opening parabola, upward opening quadratic, if a is positive. Okay, and again, the steepness stuff still matters. So like if a is positive and really big, then not only is it really steep, but it is also happy face. If a is still positive, but it's really close to 0, it's wider, but it would still be happy face. It would still open upward. And conversely, if a is less than 0 or negative, sad face. Okay, that's where we get the frown version of it again. And again, steepness applies the same way. The bigger a is, but negative, then it's all the steeper. It'll drop all the faster. It'll be pinched tighter. Or if it's still really close to 0, like a fraction, but still negative, it still opens downward. It would just be a little bit wider. Okay, and again, you can see I did that over here in the margin. I gave you some positive ones, these pink ones, a steep one, a shallow one, and then these orange ones represent the sad face, or the negative, downward opening ones. Okay, so you will get several examples where it asks you to graph various functions. Okay, in these notes, you are given these 4 functions. I have these in the solutions. I'm not going to go terribly deep in them, but you can see how various different a's, various different coefficients times x squareds will affect the shape of my u shape. Okay, negatives will open downward, positives will open upward. And then one last thing, you'll get a couple of questions that ask you for some key terms. I just want to go through these one more time. You'll be given a graph. It'll ask you to identify vertex. So here's my suggestion in your notes, just off to the side, like what will my answer of a vertex actually look like? Okay, the vertex again being the extreme point, whether it's the valley, the low point of a happy face, or the peak of a negative, right? The peak of a negative where it's the high point, whatever it might be. The vertex is actually a coordinate point. So I should get some XY coordinate point for vertex. So again, your notes, vertex should be a coordinate point. The AOS, again, stands for Axis of Symmetry. Typically, Big Ideas will actually spell it out for you, but I abbreviate it because I'm lazy. Anyway, Axis of Symmetry will always go through the vertex. Easy enough to draw, but what will my actual answer be in Big Ideas? What will my actual answer be? Axis of Symmetry is a line. And for us, for our intents and purposes, for functions, the name of this unit for functions, my axis of symmetry is going to be a vertical line. Okay, and so I'm going to get the equation of a line for my axis of symmetry, and because it's vertical, it'll always be x equals something. So for axis of symmetry, it's always going to be x equals something. That something will be basically where is the vertex located. So like this one right here in this example, the vertex is at -1, right? Went one to the left. So my mirror, my vertical axis of symmetry would go through x equals -1. Okay, axis of symmetry will be a line. And because it's a vertical line, it'll be x equals something. Domain and range we've come across before. I'll just remind you again, domain refers to how far left or right does this graph go. Okay, the furthest left, and here's just like your quick spoiler alert, all of these types of parabolas, all these quadratics, domain will always be all real numbers. Okay, just like with absolute value functions before, this will always go forever to the left as well as forever to the right. There is no limit to what x can be, no limit to what I can square, right? Range, on the flip side of the coin, will be how far up and how far down will this graph go. This one will be a little more interesting, just like it was for absolute value functions. Obviously, this one, since it opens upwards, it's a happy face one, it goes forever upwards. So there's no limit to the upper end of the range here. But the lowest that this parabola goes is it goes down to. So in other words, the range here would be y is everything bigger than or equal to 2. And I say or equal to because that's definitely a closed point right there. It includes that point. Okay, so domain is how far left or right can it go. Range is how far up or down can it go. This will be one where it's limited. Okay, it'll be y is greater than something if it's an upward, positive, happy face parabola. It'll be y less than something if it's downward facing or negative. Okay, and finally, increasing and decreasing. That's the same thing we talked about here. All these parabolas will have some sort of decreasing side or some sort of increasing side. What it's looking for here is, again, it's looking for an inequality. Basically, it's saying like, all right, well, now I'm talking about left, right for increasing and decreasing. So this is when, like, whenever x is less than -1 here. So basically, this left-hand side of this parabola, when x is less than -1, this is all decreasing. Decreasing, reading it like a book left to right, that's the decreasing half. This part's the increasing half, so that for increasing, I would be putting that when x is bigger than or greater than -1. So this half of the parabola, that's the increasing side. So you're going to come across those key terms. You'll see that in a couple of the problems. That's just our general overview for quadratics. So I'll go ahead and stop recording now.